The biggest AI models need thousands of dollars worth of GPUs, and they cost a fortune to run. But what if you can make them a lot smaller and run them for a lot less of the money and almost lose no quality? Quantization, distillation, and pruning are three techniques that can be used to make a model smaller and make them perform a lot faster without losing a lot of quality. All three of these methods make a model smaller. First, let's start with quantization. So every single number or parameter weight in the model is stored with high precision, which just means there's a lot of decimal places. To be exact, a lot of models store up to 32 decimal places. Quantization is just rounding. So, for example, the pi 3.14159 would round to 3.1 or something. But it's not going to round this much. In actuality, it rounds a 32 decimal place to 16 decimal places, which is pretty close, and it uses way less memory because to store 32 decimal places takes up double the storage than 16 decimal places. So it's like having the model size without losing quality. And honestly, there's little to no difference when you do quantization on these models. Next is distillation. You're training a smaller copy. So let's take a massive, brilliant model and then have an empty small model. And then what happens is that the small model learns from the bigger model's outputs and reasoning. So you pass inputs through the big model, and then you give the small model, which is empty, you give it these outputs, and then it goes backwards to see how the larger model got this answer. So of course, the smaller model won't be as good as the bigger model on everything, but the more you train it, the better it gets at it, and it'll be pretty close. Last is pruning, which is like removing dead weight. Neural networks are huge and are billions of parameters, as we stated before. But a lot of the connections contribute nothing, which means the parameters are almost zero in value. And pruning identifies and removes these almost zero values. And it doesn't really affect the model because it's just like rounding it down to zero. Using any of these techniques can make your model smaller without losing quality. All three techniques are pretty good, but quantization is the most impactful one. It's always the first thing to try because it's pretty easy to do, and it also makes the models a lot faster. And also, quantization is usually the one that is used by even the biggest companies. A lot of bigger companies offer their open source models with a quantized version already ready for you to download. The techniques we just covered are about making our models smaller, and this is so that they can perform faster. But there are other ways to make it perform faster. Caching and batching don't even touch the model at all. They just make the infrastructure smarter and they utilize it smarter. First is caching. There are two types of caching. First is prompt caching. Let's say thousands of users talk to your chatbot, but your chatbot has a consistent system prompt. And the system prompt is a prompt given every single time a conversation is started. Whenever a user is talking to the chatbot, the system prompt remains constant. And it's something like your helpful customer support agent for blah, 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 blah. And this prompt is repeated at every single request. So why would the model have to embed that prompt every single time the user requests it? Instead, you can process it once, cache the result, and then reuse that embedding over and over again. And Anthropic's API supports this natively. And this can save a lot of money because you're not embedding the same thing over and over again. You're saving a little bit of embedding in every single request, and this cost adds up. It's also semantic caching. If someone asks, "What's your return policy?" and then gets an answer, and then another person asks, "How do I return something?" about 15 minutes later, that's basically the same question. And a semantic cache recognizes the similarity and then returns the cached answer without hitting the model at all. So then there's zero latency and zero cost for the second request. This is a pretty easy optimization because it's just one setting change, and there's no downside to putting this setting on, so you get instant savings. Next is batching. When a GPU processes a request, it makes a little bit of space for that one request, and the rest of the GPU sits idle, so it's not using 100% of its power all the time. So if a GPU is handling requests one by one, it's not using all of its power, it's only using a small amount that's needed for that request. So, instead of sending requests one at a time, you would send multiple of them at once. And once you have these ones simultaneously, then less of the GPU sits idle. And the idea is you don't want too much of the GPU to be idle, because if it is, then you're not utilizing the GPU to its full power. You're paying for the GPU while only using about 5% of it. So batching in groups makes multiple requests together and you process them simultaneously, so then you use more of the GPU. Continuous batching is the modern version. Instead of waiting to collect a batch, the server dynamically adds new requests. So what does this mean? So in traditional batching, you would send 10 requests at once and you couldn't send the next 10 requests until all 10 were done. But in continuous batching, if one of the 10 are done, it puts another one in place for the one that was just finished. So it adds requests whenever there's space. VLLM and TGI are both inference servers that can do this automatically. Both these changes are simple, especially if you're using an inference server that's compatible with these. All you have to do is flip a switch and it turns on, and you save a lot of money by doing either of these. The last concept we're going to go over in this video is speculative decoding. So the problem is that LLMs generate text one token at a time, and each token requires a full forward pass through the model. So for a big model, it would take a lot of time because it would have to go through a lot of layers. And for each response, you have to generate a token and then wait for the next token, and then wait and wait and wait. And this would take a really long time for larger models. So speculative decoding is just cheating this process. So what do I mean by this? You will have two models instead of one, a small fast model and a bigger smarter model. So step one, the small model will start sprinting ahead. And because it's smaller, it'll be able to generate tokens faster. So it quickly drafts maybe the next 10 tokens. And then the draft might not be perfect, but it's a pretty reasonable guess. Then the model checks all 10 of these guesses. But it doesn't do it one at a time like if it was generating 10 tokens. It takes in these 10 tokens all at once in a single forward pass. And it accepts the ones that are correct, which is a lot of them, and then fixes the small bugs. And the big model doing one verification pass is a lot faster than doing generation of these 10 tokens one at a time, because instead of doing 10 forward passes, you're just doing one. And you get a lot faster generation with zero quality loss. And the final output is almost guaranteed to be identical to what the big model would have produced alone, but just at a faster rate. So those are all the main optimizations. As you can see, they all make edits in some way, but the goal is to make the model run faster and cheaper with little to no quality loss. We talk about quantization, distillation, pruning, caching, batching, and speculative decoding. This is the last lecture video of this course. Now you understand what AI is and its foundation, you know how to use AI, you know how to build it, and you know how to scale it, and now you know how to finally optimize it. And scaling and optimization are the two steps that most people don't know. Everyone does steps 1 to 3, but after building it, they don't know how to scale it and they don't know how to optimize it. Now you know the key to building optimal AI applications.